मैं 1 मिनट स्टार्ट करता हूँ. I'm sorry कि मेरी वजह से देर हो रही है, but sometimes the windows take a lot of time to update, so probably I have a backup drive which keeps updating which keeps copying dumping the whole stuff. So probably it was scheduled for Friday, so that's why it's taking so long. I'm so sorry about this.
We also faced about 10 minutes of delay just because of YouTube streaming in the opening session. You can just present your screen and see if that happens.
Yeah, I know it is still taking time. That's the problem I'm facing.
So shall we go with the next speaker?
I think you can go ahead with the next one because it's still sort of very, very slow. So it's better you go ahead with the next one.
He's getting ready probably.
So we are taking the next speaker. After that, then we can just tell.
Yeah.
Meanwhile, I'll just have the details about what we had yesterday and what we are going to have today. Yesterday, the session was inaugurated by Dean Faculty Affairs, Professor Kunal Mukhopadhyay, and our star sir was also here. We had a very interesting lecture by Dr. O.P. Pandey on dinosaur extinction and the Earth rhythm. Then we have another very good lecture by Professor Malay Banerjee from IIT Kanpur. Then IIT Guwahati, Professor Siddharth Pratyam Chakravarti has given a credit risk analysis lecture. That was also full of knowledge and was a new thing for the mathematicians, at least here in the hall. Then we had a very good, I will say the best, almost best lecture on the day, Professor Alexander, and he is a very, very knowledgeable person probably, and he gave in detail about the theory of delay differential equation. Then from IIT Bombay, Professor Vetrival has given a basic lecture on convex optimization, and that may open the door for machine learning enthusiasts, and they can develop this area, how they can use it in the using the machine learning techniques. Then we had a very good lecture of a senior scientist from National Institute of Oceanography, and I think Dr. Shantanu Pandey, ISC, some organization is there. Then we had Dr. S. Chakravarti from the IIT Mesra Mathematics, who has written many books on statistical analysis of music. So, and today we are having the lectures by Dr. Vineet K Gahalaut from NGRI Hyderabad, which is a very you can say top organization of using the geological geosciences in India and abroad. Then we have Professor Petr Girg on P-Laplacian mathematical models of fluid flow in the porous media, experiments on real media, maximum plus numerical simulations. Then we have a lecture on Dr. Ankur Kanojia for optional pricing, financial analysis. Then after the lunch also we start with a very good lecture on machine learning, support vector machines for pattern analysis. It's a very good, it will be very informative for all the students of IMSC. Then we have Professor G.K. Panda, arithmetic progression of squares with square common difference. Then we have two in-house lectures by Dr. Prof on fuzzy optimization and Dr. S. Javi for study of unplanned changes in vehicle mass model. So a wonderful day ahead. So we are just having some technical issues at the speaker's end, and we are trying to take the next speaker, Professor Petr Girg, who is also joining from his laptop. Initially, he joined with the mobile, and we are just waiting for him to present this.
Yeah, please go. Yeah. Peter, request again.
Dr. Peter is about to join using his system. We have a good number of students also today, about 50 already in. Yesterday we had a class, even then we had about some time, I think about some 10 seconds. You can share your screen, we will be seeing you and informing. Yes, we are seeing it. We are seeing it.
Got it.
Yeah, it's on the screen. You can go ahead.
Can you see it?
Yeah.
Yes, we are seeing and listening you very clearly.
Yeah, so this is my big pleasure to speak in your conference. I thank very much for the organizers to invite me. So in my talk, I would like to say something about mathematical models of the fluid flow in porous medium. We did also some experiments on real media which are used in civil engineering. And then I would like to mention some recent results about the maximum principles for this kind of problems and the impact of these maximum principles on some let's say problems from practice, and I would also, if time will permit, show some numerical simulations. So this is a joint work with Jiří Benedikt, Lukáš Kotera, Petr Takáč, Daniel Veselý, and Zdeněk Veselý. So at the beginning, I will explain what I mean by porous medium. So porous medium can be, for instance, gravel or sand. So it is something which is typically made of some type of grains, and there are spaces between these grains, and the fluid can flow in these spaces. So the problem is that in a porous medium, you have a very complicated net of channels between the grains. So it's impossible to study it by using Navier-Stokes equations. So we need some simplified tractable model which we can study. So for that reason, we have to return to pre-Navier-Stokes times, when the people were modeling flows in channels and ditches and pipes without using the Navier-Stokes equations. So they introduced a variable which was called hydraulic head, which is the hydrostatic pressure divided by the density of the fluid times acceleration due to gravity. 1 second. So can I one?
You have to share your screen again. You have to
Yes.
share your screen. Go for the right corner down.
Mhm. Yeah. So this is to explain what is that.
Share your screen. Please present your screen again.
Can you see it?
Now, wait. Now we are able to see. Yeah, please.
So this is the hydraulic head. So I'm going to explain how it works. So if you imagine a tank, which is placed on some, let's say, on some sink, and here you have the ground. So, and let's say this will be filled by water. So if you place here a tube, then the water, and you will neglect the capillary effect. The water will always rise to the same level, which is the level of the free surface. And actually, this H is this level. It's the distance from here to here, because this will the Z is measured from here. It will be Z, and here is his pressure. So this is actually this value, and here the Z is this one, and of course here the pressure is different because it's not that deep. So it again will be the contribution of this will be this term. So the H will be always this level. Now, if you imagine a slope, if you have let's say pipe, and water is flowing in the pipe, then if there will be no friction in the pipe, and you put here a so-called pitot tube to measure the dynamic pressure, so it will be, if it will be ideal fluid without no friction, then this will be at the same level. Here you will have to consider so-called total head, which contains also the kinetic energy, because this was static, and here you consider that the water flows. So this is so-called H total head, which is P over rho G plus 1/2 plus Z. But in the real fluid, if there is a friction, you have the so-called, so this is the total, actually this is proportional to the total energy of the fluid. So if you have friction, the energy is dissipated, so the level in the real fluid here will be lower than here. And if the flows are very slow, if the velocity of the flow is very slow, we can neglect this term. So this is what is actually done in hydrology, because this mean velocity of the flow is typically very small, so the quadrate is absolutely negligible with respect to the other terms. So for that reason, we will be using, even for the flow, we will be using this one, because for slow flows, this is a negligible term. Somehow resubmit my talk. I don't see my talk. 1 second.
It's not. Hello? It's not on the screen. Hello?
Can you see it now? It's a linear law, because it was for fine-grained sand. Oskar Smrekar was using coarse media such as gravel, and he obtained a law like that one. This was the best fit to the data. Then Forchheimer obtained some polynomial type, or also the same thing, same type. Then a lot of such experiments were carried out in Russia by Izbash, who obtained some power type law. And similar results were obtained also in Czechoslovakia by Misbach, who obtained again a power type law. In another materials, such as clays, you get similar laws, but for different values of n. This is for gravel, and this is for very fine-grained materials such as clay. So now I will derive the equation of the motion of the fluid, or not the equation which describes the motion of the fluid. So there are sometimes people study so-called porous medium equation, and they say that this is the right equation for flow in the porous medium. Some people study P-Laplacian and claim that this is the right model in the porous medium. And it's a question which one is the correct one. So I will briefly show how it's derived, and I will explain this is related if the flow is turbulent or laminar. If it is turbulent, the P-Laplacian is the right model, and if it is laminar, this equation is the correct one. So the turbulence was discovered in 1883, and this is kind of chaotic behavior of the fluid which flows in the tube, and then there are a complicated system of whirls, and which cause the energy to dissipate very quickly. So first I will show how it is with the laminar flow. So this will be equation of motion of fluid in so-called unconfined aquifer. So this is the surface. This is some impermeable rock, and here it is filled. This is some kind of gravel or some permeable rock. So here, this is the water table. So this is a dry part, where so-called zone of aeration, and this is the part which is saturated with the groundwater. So we want to analyze what's happening in this area. So this is a free surface, and the free surface corresponds to a hydraulic head, because the water exactly goes to the value of the rise to the value of the hydraulic head. So the free surface can be described by the hydraulic head. So if we analyze what's going on in this part, so this is what flows in. We make balance between what flows in, what flows out. This is let's observe that here we have velocity v1. Here we have the mean velocity, the filtration velocity v2. Here we have head h1, and here we have head h2. So what flows in is h1 times v1, and what flows out is h2 v2. We are using so-called Dupuy-Forchheimer assumption, which says that if this water table, if this angle is not too big, then the velocity goes only in the direction in the horizontal direction. There is no flow in the vertical direction. So for that reason, and the flow is constant in this all cross section. So this is so-called Dupuy-Forchheimer assumption, which was observed in the nature for relatively small slopes of the water table. So then we get, if this will be fine sand, then we can use this type of constitutive law, which was observed by Darcy, and making this algebra, we get putting this here in place of v, we get this term. So if we use mass conservation, so change in time is what flows in minus what flows out plus production of the sources. So this is exactly this. And if we go from the integral form to the differential form, we obtain this equation, which is so-called porous medium equation. So it was derived from the Darcy law, and it has been observed that the Darcy law is valid in certain range of the flow. Now using the fine laboratory techniques, they can see that this is for the laminar flow, when laminar flow occurs in the channels between the grains. So this is the porous medium equation under the which was derived under the Dupuy-Forchheimer assumption and the Darcy constitutive law. Now, if we turn to turbulent flow, then the Darcy law must be replaced by a Power law, which has this form. This is where P is typically between 3/2 and 2. If we are close to 3/2, then we are in the fully developed turbulence, and if we are with P close to 2, then it's not fully developed turbulence. There are some regions where there is a laminar flow, so it's a kind of combination. So then you again do the same analysis under the Dupuy-Forchheimer assumption, but now you place there the constitutive law of the power type. So after plugging here this formula, we obtain this term. So after some algebra, we can rewrite this term, plugging this here into this form. So it's a derivative of a power. This is gradient of the power. Here it's in one dimension, so it's a derivative of this power, and again it's a power of that. So then we can write again the mass conservation. So this is the change of the amount of the mass in this part equals to what flows in minus what flows out, but we switched sign because of this, plus the production of the sources. And after rewriting it to differential form, we get this partial differential equation. So here if we make a substitution that this will be equal to u, then we can rewrite it in this way, and this is so-called P-Laplacian of u in one dimension. This is an operator which is now very fashion to study, but it will turn out that actually this is a very old operator. This was neglected. It was overlooked that this operator is known for more than 100 years. So, of course, in the 19th century, they did not consider it like a partial differential equation. They were studying the radially symmetric case. So, first, let us see the differential equation for the well. In case of when we assume that the Darcy law holds, which is typically in the sand, fine-grained sand. So Q is what we pump away from the well, and this is the flow through a cylinder with the radius small r. So it is 2πr, the length of the circle. H is the height at that point, at that shell of the cylinder, and V is the velocity of the flow. So here we plug the Darcy law and we obtain differential equation which we can easily integrate and obtain a formula which contains logarithm. The problem is that if you take here a limit to infinity, then the limit of this term will be infinity. So it says that the water table will rise above the Earth's surface, which is impossible in reality. So if there is a steady state of pumping, then the water table must rise above the surface of the Earth, which doesn't happen in the reality, of course. So this was somehow formulated like a paradox, which was first observed in a theoretical paper by Smerker and later resolved by Zhukovsky. So I always make the snapshot of the original paper because this is very interesting how it was written at that time. So we are seeing a communication from 19th century, and using this law, Zhukovsky found the correct. So the law was actually, the constitutive law was given by Smerker, and Zhukovsky found the correct formula for the water table using this over-type constitution law. So again, the same way we will make the ordinary differential equation for the radially symmetric case. And here we have the solution is in the closed form, and here if we take limit to infinity of this solution, then we get some finite value. So it says that if we pump in certain way, the surface of the water table will be asymptotically approaching the water table before we were pumping. So another place where P-Laplacian was discovered was in case of turbulent filtration of gas by Eli Benzon. So this is a picture from Baku where he was working. So these are the oil towers when they were extracting crude oil from the earth, and also the natural gas. So actually this is related to the P-Laplacian is related to extraction of the natural gas from the earth. So it is a polytropic process when the gas flows through the rock, through the porous rock. And again, we have an equation of continuity. In case of compressible gas, which is the case of any gas, of course, the constitution law has this form, where gamma is the index of polytropy of that gas. And using this and plugging into the equation of continuity, they obtain this equation, which again contains the P-Laplacian operator. So these are the typical equations which are connected to the flow of the porous medium, to the flow of a fluid in the porous medium. I will briefly mention the experiments. So this was the experiment by Darcy, who was he had a cylinder filled with fine-grained sand. Here is a manometer to measure the pressure, and he was measuring the loss of the pressure when the fluid is filtrated through this column of sand. So he was pumping the water up, then the water was flowing down, and he was measuring the pressure drop. And he obtained this linear law. Then there were another experimentators who obtained nonlinear laws of the power type, which seems to be the most natural type. And also, this was very recent. This was from 1936 experiment by Ms. Bach. This was made in very fine laboratory conditions, and he again obtained a power type law. The very interesting are experiments by Isbash, because he wanted to study filtration when there is a really very big difference of pressure. So he was using a tower of the height 35 meters to produce very high pressure of the water, which was filtered through the column of the porous medium. And again, he obtained the power type law. So with my colleagues from universities, Zdeněk Veselý and his son, we were trying to reproduce some of these results, but we wanted to do it for real materials which are really used in the civil engineering. So these are the typical type of gravels which are used in civil engineering. Here it's the size of the grains. So for instance, this is grains 4 to 8 millimeters. These are, let's say, very fine, 2 to 4 millimeters. And we were using different types of shape of the grains. So this is crushed stone, and this is like pebble stones. And for this, so Zdeněk Veselý is from the department. He's from New Technology Center. They do physical experiments related to new technology, and his son was a student in the high school, and he did it like they call it. It's kind of scientific work the students can do in high school, kind of. So we obtained power type laws for different type of stones. We obtained different type of different type of powers and coefficients. What's interesting here is that most of the experiments had this very strange shape. There was not like a nice power, but the data were at certain point deviating from that power a little bit. So this is very interesting, because looks like the power is not enough to describe it very well. One has to probably use more complicated functions. So this is very interesting for further developing of the theory. So we should not stuck only with the power type nonlinearities, but we should study more complicated type nonlinearities, which is again somehow becoming a fashionable type of operator called P-Laplacian. So looks like the P-Laplacian is a much better approach to study the flow in the porous media. The power type P-Laplacian is like a kind of approximation of it, but if one wants to get more realistic results, one has to go for more complicated type of law. So now I would say something about compact support solutions and strong maximum principle. So let us consider the following initial value problem. it's a boundary initial value problem. So we have Dirichlet conditions on the boundary of the domain omega. We have initial condition, and this is considered in the weak sense, but there are several definitions of the weak solution for this type of problems, depending, for instance, how this function B is. So you can find it in these, the exact definitions and exact formulations you can find in these papers. So the typical weak comparison principle is that if the data are ordered, then the solutions are ordered the same way. Weak maximum principle is that you would consider the data for the first solution 0. So this will be 0, this will be 0, 0. So you will get 0 solution. So you will be comparing with 0 solution. So this means that if F2, G2, and V2 is greater or equal to 0, then U2 must be non-negative. So this is called weak maximum principle, which follows from weak comparison principle. We were interested in so-called strong maximum principle, and especially we were interested in a special type of strong maximum principle. So let this and this data are ordered in this way, and for certain values of K and M in this equation, you get compact support. For certain values of K and M, you get that if you start with a positive, somewhere positive initial condition, it immediately becomes positive. So these are actually solutions where kind of solutions, so-called self-similar solutions, where you start with initial condition to be a Dirac distribution localized at 0. So if this is satisfied, then the solutions which are at 0 for time t equals to 0, which tend to Dirac distribution localized at point x equal to 0. So if this is satisfied, then you get a compact support solutions. And if this is not satisfied, then immediately the Dirac distribution gets produce a solution which is positive everywhere in Rn. These are these pictures, for instance. So, for instance, for the model of the aquifer, we see that we satisfy this condition. So, in case of the aquifer, it will generate the compact support solution. In the case of Liebenzone equation, which was the filtration of the natural gas in the porous rock, it's quite complicated because it depends on the interplay between P, the parameter P, and gamma, which is the parameter of the polytropy of the gas. So what we were let's consider the following problem. So now we denote this way so-called P-Laplacian. So this is gradient with respect to x, not with respect to the time variable, which is treated separately. And let us consider this initial value problem with zero Dirichlet conditions on the boundary. And this is the initial condition. So we consider this function B, to be positive for positive values, C1 function, and derivative is positive for all S positive. So together with Jiří Benedik, Lukáš Kotrola, and Petr Takáč, we proved that if under this additional condition, and we need that the data are continuous, then if the initial condition is positive at some point, it means positive in some small ball, then there exists tau in this interval such that uxt is positive for all xt in this time space domain. So this means that it's not the compact type support solution. It immediately becomes positive in omega, but it will not stay for a long time, just until some value tau, because it has been established before by Di Benedetto that for P between 1 and 2, the solution have so-called finite extinction property. So they will so if f is 0, if f would be 0, then such solutions will become 0 after a finite time. But we know that for a moment it will be positive everywhere. So this is so-called infinite speed property. The proof of this is based on upper and lower solution method. It's very extremely technical, so I don't show it here. And it's motivated by this paper where they were studying similar problem on Rn. Here the main difficulty which we had to consider was that you are constructing a lower solution which has the shape of expanding wave, and you need to fit it under the solution. But if you are working in Rn, you have no problem with the boundary, but our main obstacle was how to play with if the boundary is present. So the boundary, and on the boundary we have the zero Dirichlet condition. So this was the main difficulty, to have zero Dirichlet condition on the boundary, and how to get this expanding wave under the solution. But we were motivated by this paper. So now I will explain how it corresponds to our problem. Sorry, how it corresponds to Barenbach's solution. So he found that there is finite speed of propagation if Km is greater than 1, and if K times M is less or equal than 1, you have infinite speed of propagation. So these are these pictures. This one, this is the boundary case. So in our case, because we use different notation, the modern notation is to use that P in P-Laplacian. So P minus 1 is his M. Bs is in our situation as if Bs is S equal to 1 over K, for instance, then this is hello? Yes. So 5 to 10 minutes. Perfect. So for this then this condition, which is the condition which we have here, is satisfied. So this equals to this. Sorry, here it's a misprint. So this equals to, for this choice, equals to this one, and it's equals to 0 if and only if this is satisfied, which is exactly the condition which matches the Barenbach type solutions. So we could not get anything better. So we get the optimal result in this sense. So I will quickly apply it to mathematical model of two parallel drainage ditches. So imagine that you have two parallel ditches. There is some gravel in between them, and you have a sudden discharge of water in between the ditches, and we want to study how this water flows to the ditches. So this can be described by this PDE. The derivation will be similar as I did at the beginning, and if the material is gravel, then P is between 3/2 and 1/2. So by this substitution, we can get this equation. Further, by doing another substitution, because we can rewrite U as a perturbation of the steady state. Steady state is that unperturbed level, which is the rate of the water in the case. So we find another initial value problem for W, and to this we apply our maximum principle. So we have to first write it in a certain way that, for instance, Laplacian of this one is actually P-Laplacian of W, because this get destroyed by the gradient. So finally we have this one. In a similar way, here we can add zero, subtract 0. So we can write it this way, and then we can define B to be this one. And this B will actually match exactly our assumption in the theorem. So we reveal this super solution will have to have compact support as well. Because from below it's estimated by 0, from above it's estimated by this super solution, so it must have compact support. So the conclusion to this example is interesting, that in the case of dry ditches, the water from a localized sudden recharge does not reach the shores of the ditches immediately, but it expands. It goes like a slowly expanding wave. And in contrast, if you have water in the ditches, then the localized sudden recharge causes the immediate water table rise in the entire aquifer between the ditches. So maybe I can show some. If I have like 2 minutes, I will show. We did some numerical experiments. Equation, and here is the example of the ditches with the sudden discharge. And the maximum principle allows us to use implicit discretization scheme. So we at each step we solve elliptic problem, where in the right hand side we put the data from the previous solved problem. So we are solving this initial value problem. It can be discretized. So this elliptic problem, this is the elliptic part. If we rewrite it using the implicit differentiation scheme, this is the elliptic part, and this we solve using finding a global minimum. And we discretize the P-Laplacian using finite differences. So I will show some animation what we get. So this is the solution. Because it's calculated for a long time, so I cannot run the simulation. I just show the results. So it will be running like half an hour. So this is the result of the simulation. So this is the initial. So this is after the first integration step in time. So the initial data was like a rectangular initial condition. So this is after the first step, you have some smoothing already. And this corresponds to the P-Laplacian. So when we were fitting the power type law, and this corresponds to, if we did not, to the Laplacian. So you see that the solutions differ. So if one wants to do fine calculations, one really needs to consider the nonlinear model. So maybe I think it's the time to end. I have another simulation for rain on the Iceland, but this is of the same type. So maybe I can stop at this moment and answer your questions.
Yeah, Peter, interesting lecture. Yeah.
Hello. So thank you for your attention. And if you have any questions.
Yeah, it was an interesting lecture. You have used maximum principle.
Yes.
Grassroots level, and you have come to the update level for the model you have obtained and how you have studied. You have used maximum principle. Is there any other way of studying this equation?
Pardon me, 1 second.
My question is that you have used maximum principle. No. You have used maximum principle. Is there any other way of solving that or to study the equation?
The question is, you have used maximum principle. Is there any method, any other way for solving these equations? What are other alternatives to the principle?
So, for instance, the maximum principle we use to get the qualitative information about the solution, and numerically we obtain the numbers, but of course we don't know if the numbers are correct because these are highly nonlinear equations. So we don't know. It's not much known about the convergence of the method. So the numerics is just simulation.
Okay, I understand.
Okay. Thank you, sir. Thanks for a nice talk. We are not getting any online questions. Sir, thank you again for coming so early in the morning. And hopefully our students will contact you very soon, and we make a group and work with you.
Thank you, Peter.
Thank you. Thank you very much.
Thank you
for attention.
Now I request our next speaker, who should, due to certain technical problems, I was not able to join early in the morning at 10 a.m. And now all the problems have been resolved at his end. So I would like to welcome Dr. Vineet K Gahalaut. He has been my senior at Roorkee when we were studying there at University of Roorkee. And since that time itself, we know that he has been a very hard worker. Means full of involvement in studies as well as other than studies also, he was very active. So yeah, and many few persons like me from my police department being in the hostel, we infected him at the hostel mess table. Thank you, sir, for being with us for such a long association. Dr. Vineet K Gahalaut has teaching experience at Roorkee from 1996 to 1998, and experience 6 years before that, 1990 to 1995. And since then, he has been there in NGRI Hyderabad CSIR lab from 1992 to 2015, and then 2019 he is still continuing. In between, he went to scientific management and funding experience at Department of Science and Technology, Government of India. And he has scientific science. He was scientific administrator at LCS. You can see him many times when the earthquakes come in India, and his opinion is taken on various TV channels. So, and his broad area of research is geodesy, tectonics, and seismology. Last 10 years, he has been actively involved in modeling, interpretation of geodesic data, and studies related to earthquake occurrences processes. At present, he has been involved and responsible for GPS measurement of crustal deformation in Andaman Nicobar, Northeastern, Garhwal region, Koyana region, and Godavari region. As a director at NCS, he was responsible for earthquake monitoring of Indian subcontinent using 150 observations, other than taking up several research problems. He has plenty of awards, Fellow of Indian Academy of Science, Bangalore, ISES Get Merit by Institute of Seismological Research, Ahmedabad, Anit Alwani Memorial Prize, Gold Medalist for Indian Geophysical Union, Physical Research Laboratory Award in Earth and Planetary Sciences, MS Kannan Award, Gold Medal by Indian Geophysical Union. CSIR, he earned Young Scientist Award, which is a very prestigious award 2001. Indian National Academy INSA Medal in 1997. UNESCO Fellowship, and he worked in Italy in 1991. He has more than 120 research papers to his credit. So, with that brief introduction, I would like to request, sir, that please kindly share your PPT and let's get enlightened with your presentation. Sir was initially a little hesitant about addressing mathematicians, but I requested him, sir, that we'll be at least knowing something where we can go and see the application of mathematics. Thank you, sir. Kindly present your PPT. Sir, your mic is mute.
Yes, I'm sorry. Thanks, Piyush. Yes, I was hesitant to to talk in front of mathematicians because I mean my knowledge of mathematics is very poor. That's one subject which I mean I used to like it, but I was kind of I was more into physics, more into those kind of things. But then with time, with during my PhD, then I realized that that's what my teacher told, that look, you have logics, you have science, you have physics to explain theorems, you have physics to explain laws, all laws, but then ultimately you need a script, you need to write it on the piece of paper, and that's where the mathematics comes in. If you cannot describe any law or any rule through a mathematical equation, then it's not a rule. So you need to put it somehow on piece of paper. So that's why the mathematics is important. And I'm sorry that I couldn't join early because there was some issue with the with the upgradation of the upgradation of the system. Probably it was due for Saturday, so that's why it took a lot of time. And thanks, Peter, for accepting the request to join early. Porous elastic, the flow through poroelastic media is one of our favorite topic in seismology, because he was talking about flow through a ditch or through channel, and that's what exactly we do in case when we have a fault zone in which fault zone which is going deep, and we talk quite a lot about a role of fluids in earthquake occurrence, and that's where flow through porous media becomes important in case of seismology. You might have heard a lot of work, a lot of earthquakes occurring in Texas and several other places, Oklahoma, which are basically earthquakes caused by fluid intrusion, earthquakes which are caused by injection of water, brine water, to extract more oil. So that's where the role of fluid and flow through porous media becomes very important. So I enjoyed your talk, Peter. Thanks a lot. Thanks very much. Of course, I couldn't understand much because I lost the first 15-20 minutes in the beginning. So I'll start my talk now. Let me share it. Can you see the talk?
Yes, sir. Yes, sir, it's there on the screen.
Okay, so that's what I'm going to talk: mathematics of elastic dislocation and rebound theory in seismology. Please excuse me again if I speak something wrong, because my knowledge is again very limited in terms of mathematics. We use mathematics which is kind of outdated in your jargon, kind of outdated in your subject, because we are mainly looking for application of mathematics into seismology or earthquake occurrence process. So that in that way, my knowledge could be slightly old, but nevertheless, I'll try to impress upon that how we have adopted mathematics and physics in seismology and in earthquake occurrence process. You might have yesterday there was an earthquake in Kazakhstan, and that occurred something around 10:30 p.m. in the night, and there were lots of issues which were raised in the media. There were lots of I was awake till 1 o'clock, 1:30, and the reason was that this earthquake was felt wide over, right up to Delhi region. I'm not sure whether anybody experienced this earthquake in your institute at Mesra, Ranchi, but I'm sure that people in Delhi they experienced it quite vigorously. And this was also experienced quite vigorously in places like Amritsar and Srinagar. And it so happened that there is something called auto-location software, which is used to locate these earthquakes. So it is basically a it's not exactly machine learning, but it's more to do with pattern recognition. So it keeps looking at the phases of earthquake waves, and then it tries to it tries to locate earthquake, and it tries to look at certain features in the earthquake waves. And it so happened that this auto-location software, first it located earthquake in Kazakhstan, which was correct, although the magnitude it estimated was very high. They estimated a magnitude of 7+, and then they also this server, it also located an earthquake in Amritsar. It also located an earthquake in Srinagar, and these were all fake events. These were not actually the earthquakes, but it so happened that the software picked up the wrong phases, and it located the earthquake as an earthquake in Amritsar or as an earthquake in Kashmir, and that caused lots of panic. And that's when I remembered that I need to give a talk tomorrow. And probably this is a very good example to emphasize on mathematics, the application of mathematics in seismology. And then I was reminded of one book, which is a very old book. This was probably written in 1970s or 80s, I remember. And you see here, there's one author, which is his name is Professor Sarjeet Singh. He was the professor of mathematics at Maharshi Dayanand University, Rohtak, and this is considered as one of the very standard textbook in seismology. It's one of the he is one of the best seismology who knew mathematics, who was basically a mathematician worldwide. And I mean, we have huge respect for him, for Professor Sarjeet Singh. And this book was taught to us, I mean, was referred quite extensively in our master's degree program, and it's referred all over the world in all universities. So and this book talks about seismic waves and sources, and that's what precisely the auto-location software which I was talking about does. That it tries to identify the sources, earthquake sources, which could be of different types. I mean, depending upon what depth they are occurring, what is the mode of deformation, what is the mode of slip, what is the dip of the plane, there's several factors which come in, and every earthquake has got and then because of this elastic media, you have waves which are of different types depending upon their particle motion. They travel at different speed, so that's why the radiation pattern of all these waves is different, and hence you feel these earthquakes differently at different locations with respect to the earthquake epicenter. So this book talks about seismic waves and sources, earthquake sources, and it is one of the most standard textbook. But I will not go too much into detail of this. But I just thought that I to draw your attention towards this book. He still, I mean, he has got a lot of students even now. I'm not sure. I hope that he's still there in Rohtak, but he has a lot of students who keep working on these problems, on elastic medium, poroelastic medium, viscoelastic medium, propagation of waves and seismic sources. So with this, I will start my talk, and I would like to draw you something different. So when you go to a mountainous region, for example, Garhwal Kumaon region, or whatever close to you, you see some rocks around you, and it may happen that you may tend to ignore them, but these rocks, they tell you quite a lot about the forces which they have experienced, the process through which they have gone through. For example, if you look at this figure to my left, you see these rocks, and then you see some rock folding here. So that you imagine, or I mean, consider this, that all these rocks, when they were deposited, they were all flat, but then these rocks were deformed to an extent that now they are taking this shape. Now try to pick up a rock from this, from any rock, from any road cutting, and try to fold it, try to apply force on it. You cannot bend it, you cannot fold it at all. So imagine the kind of forces which were required to fold these rocks, to bring them to this shape. Now to the right, you see another road cutting in which you see a fault here. We call it as fault, and you see that there is a discontinuity on the continuation of rocks on this side and the rocks on that side. So now again, I'm saying that you pick up the rock mass and then try to break it. It's almost like impossible that you can break it. But imagine the forces which were applied on these rocks, which led to this folding here, bending of these rocks, and which also led to the fracture of these rocks. We call them fault, which might have created earthquakes as well. So all this nature, I mean, when you go to next time when you go to Himalaya, please try to look around and imagine the trauma through which these rocks have gone through. The forces forces of several thousand bars or kilopascal, which was applied on them. The temperature, they might have, it is possible that they were not here when they were deposited. They might be at surface at great depth. So imagine the overburden pressure, since when you go at depth, the temperature increases. So imagine the temperature through which they have gone through. So imagine a rock which has gone through tremendous pressure, temperature, and then forces, which has brought now which you see on the surface, and you see them in different form and different shape. So that's from where the geology started, and that's from where we started thinking about forces. That's from where we started thinking of physics, and that's where the mathematics came in. You also there is when you go to Gujarat, when you go to a place called Allahabad, which is at the border of India and Pakistan, you see that the land is really flat here, but then you suddenly see a jump in topography, which is almost like 6 to 8 feet, or in fact, at some places it is more. And then there are documents which suggested that this we call it bund, there are a lot of bunds which are natural made, or which are made artificially by people. I mean, dam. These are basically, bund means dam. So it was said that there was an earthquake in 1819 at India-Pakistan border. Of course, in those days it was only India, and which caused this land to uplift. So this was basically a fault along which the rocks on that side moved upward, and then a bund was created. And this bund was so strong, the original height was very, very high. It was almost like 10 to 15 feet, that it dammed the river. And that's why the people, local people in that area, they called it as Allah Band, a bund created by Allah, by the God. So that's why the name Allah Band came. Now, that was probably for the first example when people in all over the world realized that the forces exerted by these rocks, these are the forces exerted by released by earthquakes, they can cause land to deform. They can cause land to move upward, and that's when the investigation of earthquake sources started. But then, of course, a lot of work was done by people like Jeffries, people like Bullard. But then, even then, we were not close to understanding earthquakes. I give you a beautiful example here. This is a recent earthquake which has occurred in New Zealand. It's called Kaikoura earthquake. And if you see, you don't need to be a geologist to interpret this. You can clearly see that there is a fault here, and this road was absolutely straight before the occurrence of this earthquake. But then occurrence of this earthquake, it led to the uplift of this part, and also shifted the land on this part in that direction. So this again confirms that these earthquakes, they release huge amount of forces which deform the rocks and which deform the landforms, which modify the landscape. In fact, what I keep saying is that when you go next time to Himalaya or any other place, when you see topography, when you see these rocks which are folded, when you see these faults, so don't just think about the beautiful landscape, but also think of that the process which is responsible for causing these rocks to go up. And the process is essentially the earthquake occurrence process. Of course, there are other factors, for example, erosion because of wind, because of water. But then tectonic forces or the earthquake occurrence process is. But then this was a recent example. But then we didn't know this until 1819 was the first evidence when we learned that these rocks, the earthquakes modify topography. But then it was only until an earthquake which occurred in San Francisco in 1906, when a fence, which was a straight fence, continuous fence, there was a fault here, and it got offset almost by 6 to 8 feet. So this fence, which was continuous, it got offset by 6 to 8 feet. Now this was a revolution. This was, the studies which followed this led to revolution in seismology. This was such a simple observation. And then the theory of elastic rebound came in. And the theory of elastic rebound says that, look, so this was the energy which was released by the earthquake. It may sound very simple now, but in those days, it was considered to be a revolutionary theory. So the theory says that, look, since the earthquake have caused this deformation, earthquake has released this energy, and cause this deformation, cause this offset. So this implies that this energy was accumulated in previous years during the preparation of this earthquake. So that means the earthquakes on a fault, energy gets accumulated over time, which is released during earthquake. Now, this was such a simple thought, but nevertheless, it took a lot of time to understand it. And it was only in 1906, 1910, this elastic rebound theory was given. And even now it is considered the basic tenet of seismology all over globe, elastic rebound theory. And what it says is that, look, this is a small video file. So what it says that you have suppose you have an orchard or roads. So now the force is building up on either side, and you see now earthquake has occurred. Of course, some oranges have fallen. I can play it again, and some oranges have fallen because of an earthquake occurs. And then you see that the road or this has been offset, right? And that's nothing but the elastic rebound theory. Now, to put it in graphic form, or to put it in the fence kind of thing. So this was so that you are applying force on either side. So that's the plate tectonic force, and then you are bending it because of you're continuously applying the force because there is friction along this surface. So you're not able to break it because the strength is very high. So you're continuously applying the force, and then it is getting bent here. And then when the strain exceeds the strength of these rocks here, then the offset occurs. That's when the earthquake occurs. This was such a simple theory, which forms the basis of seismological work even today. And that's where the elastic dislocation came in. And elastic dislocation basically came from fracture mechanics. I'll go to that a little bit later. But actually, this was put in a very simple manner. But the way it happens is like this: that you have these straight lines here. This is a fault. You're applying forces on either side, and then you are bending it. And then once you're bending it, and then the earthquake occurs. And earthquake occurs in such a way that there's more deformation close to the fault or close to the epicenter, but then the deformation decreases as you move away from it. Now, if you actually sum this with this, you get this. And what I mean is something like this. So that means when you are applying this force, we're applying these the force on either side. These are not experiencing any strain here. These pathways or these roads, they are following the force. They're moving as you have applied the force. So if I actually see that how much strain has accumulated here, then what I'll do is I will join this line straight here. I'll join this line straight here, and this black portion here is the strain. So that means this part has accumulated strain corresponding to this much of due deformation, and this here right here is this much corresponding to this much of due deformation, and that's what is recovered during the earthquake. So you have strain accumulation and you have strain recovery, and when you sum them up, that's when you get that's what you get offset. Now this was important. Elastic rebound theory was important because then we realized that means before the occurrence of earthquake, I can monitor this strain. I can monitor that how these rocks are deforming. I can monitor this strain which will be recovered during the earthquake. So these are all in the first phase we thought that we considered them as elastic strain, and we thought that since these rocks behave more or less like elastic rocks, elastic material, we can actually measure this strain, and we can actually identify the regions where the strain is accumulating. And if I know the yield point, then I can probably also talk about when the next earthquake is going to be, where and when. Of course, I mean, this theory was given in 1906, 1910, in fact, and even now we are not nowhere close to earthquake prediction, because now we understand that there are a lot of other things which go in understanding earthquake and in predicting earthquake, and in understanding the source and medium of this region, of any region. So we're still nowhere close to it, but nevertheless we have a basic theory which tells us that, well, you can actually monitor the strain accumulation in a region, and that's what we do all the time all over the globe. Well, that was the starting point of seismology, the real seismology. But the real seismology came into picture when the theory of plate tectonics was proposed. Theory of plate tectonics came into formulation in 1960s. So imagine that and that's when the real seismology started. Real understanding of earthquakes started with the elastic rebound theory and with the plate tectonics. So this subject, which I'm talking, which the seismology, this earthquake occurrence process, is extremely young in that sense, that we started understanding things only after 1960s. And the way plate tectonics was, of course, there are a lot of people who contributed towards plate tectonics. People started looking at continents, the shape of continents, how do they fit into each other. They started looking at fossil in different continents. But the real breakthrough came at a very sad period of time, World War II. So that's when a lot of in those days, it was all, all the journey was mainly done by ship. And this was also an opportunity to do a lot of science. You might have noticed that a lot of discoveries were made during World War II. And one of the discovery was partly the plate tectonics. And what people were doing is that when they were taking these ships, they were because in those days navigation was done using compass or using astronomical observations. So people were doing a lot of magnetic survey while moving in the ship. So all army, all British or US or Japanese, mainly British and US ships were all loaded with magnetometers, and they were continuously monitoring the magnetization of the rocks. I'm sorry. During the voyage, and what they found was that so there's something called mid-oceanic ridge in the oceans. So what they found was that at some places you have magnetization of the rocks in one direction, and then suddenly after some time, after some distance, the direction of magnetization changes, the white one, and then again the magnetization comes back in the same direction. This is nicely shown in this figure, in which the magnetization here is north is this direction. So this magnetization is in this direction, but then on this strip away from this mid-oceanic ridge in terms of distance, the direction of magnetization is totally different. It's just opposite. And that was the breakthrough. We knew that yes, there was a theory called continental drift theory, which was telling that look, these continents, they keep moving, they keep drifting, and they drift because there's something called mid-oceanic ridge, which keeps pumping the lavas or magma upward, and which keeps pushing these two plates on either side. And as the lava freezes, it freezes the magnetization is as per the direction of magnetization at that point of time. And we know that the direction of magnetization keeps changing over a period of a few million years. So then we saw that, okay, as you move away from it, the age of rock increases, and the magnetization also keeps changing from place to as you move away from the mid-oceanic ridge. So that means these mid-oceanic ridges are continuously creating crust and pushing these plates, and that's when the real plate tectonics came into picture. So it was the combination of plate tectonics and elastic rebound theory, which led to our understanding, which led to such a huge understanding in earthquake occurrence process, what we do today. So just to tell you how these mid-oceanic ridges look like. So if you look at any Google map, you look at Google Earth and look at these continents and these oceans carefully, you will clearly see that there's some high topography within the oceanic region. So these are nothing but the mid-oceanic ridges. In case of India, you see that this is mid-oceanic ridge. This is called Avans fracture zone. This is called these are Indian ridges here, and then it joins here, joins with the ridge, the mid-oceanic ridge in Pacific, and then it goes down like this. So all these ridges are the spreading places where the plate keeps building up continuously, and then which keeps pushing these continents or these plates. We prefer to call them as plate. So these plates, they keep moving, and that's where we have this Indian plate here. And it's because of this the continuous lava or the magma which is coming out, which keeps pushing these plates. In case of Indian plate, it moves towards northeast at a rate of about 5 centimeters per year, and then it collides with a plate which is called as Eurasian plate here, which has led to uplift of the mountain chain here, which we all know as Himalaya. So now the moment we understood plate tectonics, then we started putting lots of seismometers, lot of earthquake monitoring devices, and this was again a big kind of surprise. That look at now these bright green, yellow, red dots. These are the earthquakes. These are the earthquake epicenters. Now compare this figure with this. All these earthquakes are occupying here, the mid-oceanic ridges. So that means all these earthquakes are occurring at mid-oceanic ridges here, which are the spreading centers. And then a lot of earthquakes occur at the convergent plate margin. That's where the two plates collide. That's where one plate undergoes the other plate, and that's where a lot of big earthquakes occur here. And that's why we have lots of earthquakes in the Himalayan region or in Andaman Nicobar region, because these are the convergent plate margins. We have earthquakes here, but these are all very focused. These are very small earthquakes. They are not very big because of high temperature. The rocks cannot withstand high strain, and that's why they break easily in small earthquakes. So that's these 3-4 things together led to our great understanding in earthquake occurrence process. So that's how the Indian plate moves. It moves towards northeast at a rate of about 5 centimeters per year. Let's move further. And it's this movement which causes earthquakes in Himalayan region. For example, the 2015 Gorkha earthquake, which happened a few years back, which caused, I'm sure that people in Patna, Jharkhand must have felt this earthquake quite strongly in 2015 in April. So that's why you have earthquakes here in Himalayan region. You have earthquakes in Indo-Burmese Arc. This map is slightly oriented in different direction. So the north is in this direction here. And if I make a cut here, if I'm making the foundation for my slightly mathematical part here. So if I make a cut here, if I cut this vertically, and if I try to look inside, then that's how this region look like. So these are all Himalayan mountains, and this is the Indian plate here, which is subducting or which is colliding with the Eurasian plate here. We call it as Himalayan wedge, and that's the fault along which the contact surface between the two, which produces all these earthquakes, where all these earthquakes, big earthquakes like 2015 earthquake or 1934 Bihar Nepal earthquake or 1905 Kangla earthquake, all these earthquakes, they occurred here. So all these earthquakes, they mostly occurred in this region. So that's the fault on which which is considered as the most dangerous, or which has got high potential of generating big earthquakes. We call it as main Himalayan thrust or detachment, decollement. There are several names to it. Because of high temperature further down, temperature reaches more than 400 degrees centigrade. The rocks are more like ductile, so they don't strain. They don't store strain. So that's why the motion is mainly occurs in ductile manner, and that we call it as a seismic slip. So it does not generate earthquake. The earthquake generation in this part below Tibetan plateau at depth are very rare. You don't get earthquakes at you do get earthquakes at shallow depth, but not at depth of 40-50 kilometers. So that's the basic theory of earthquake occurrence, basic process by which earthquake occurs in the Himalayan region. And if I use all my knowledge of what we learned in elastic rebound theory, plate tectonics, earthquake occurrence, then I can draw a graph in which I'm showing time. So I'm saying that all these plates are moving and all these rocks are deforming. So they deform and then they break, they deform, they break. So you have period of strain accumulation, period of strain release, and that's what happens here. So you have period of strain accumulation, and then earthquake occurs. That's a period of strain release, and of course there is a period of what we call as non-linear deformation. Because of sudden release of strain, the temperature becoming higher during earthquake occurrence because of friction of the rocks, and the material below this elastic lid, where these faults are, the material below it in the mantle or in the lower crust is kind of viscous. It behaves more like, it deforms more like in non-linear fashion, time-dependent manner. So that's why the deformation immediately after earthquake is kind of non-linear. We call it as post-seismic deformation. But essentially there are two phases here. One is the period of strain accumulation and the period of strain release. And these are essentially or largely elastic deformation. And that's where the concept of that's where the elastic dislocation comes in. So to summarize all this, when you see the mountain topography build up, that's because of plate tectonics, and plate tectonics causes deformation. Deformation occurs through earthquake cycle, and this earthquake cycle leads to topography build up. So that's one thing which I want you to appreciate when you go to the mountainous region, when you see a topography, when you see mountain, even in Peninsular India, even in Vindhyan region or Satpura region, Aravallis. So that means these rocks which are uplifted, which you see now at surface, they have undergone through all this process, along with other processes, for example, erosion, fluvial process, water, climate change. But of course, plate tectonic is one of the most important process which has led to the development of mountains or topography buildup. And now coming back to the mathematics of it. So this was after understanding the plate tectonics and understanding the elastic rebound theory. there were 4 questions which were formulated in mathematical seismology. And these 4 questions were problems of theory of seismic waves, which we still sort of deal with, inhomogeneities in the media and other causes, and to new methods available for study of interior of Earth. To understand the earthquake sources, I mean, we still don't understand the earthquake sources in full. I mean, earthquake is not an explosion or an implosion. It involves, it has got lots of intricacies. I'll come to that a little bit later. And then, of course, problem of instrumental seismology as to how to build these instruments so that we can reliably record the ground motion. This we have sort of understood quite well, and we are quite successful in designing these instruments. We are also quite good in understanding the response of these earthquakes onto the buildings, and that's why there's a lot of emphasis which we keep giving on making earthquake resistant construction. We cannot predict earthquake, but we can make these structures safer towards earthquake. So that's why there's a lot of emphasis which is given on engineering seismology. And then, of course, this is another. So problem 1 and problem 4 are still kind of developing. The problems of statistical seismology, that if we keep saying that this process is quite of quasi-linear or quasi-periodic. So that means we can do a lot of statistics on seismological data, and we should be able to have predictive model for these earthquakes. And that's where a lot of periodicity problems come in. I mean, people keep looking at the earthquake distribution as normal, Poisson, Rebound, different kind of distribution of earthquakes, to know whether we can predict these earthquakes, or we can get an idea of occurrence of earthquake probability in near future. So there's a lot of work which goes on in problem 4 and problem 1. And I'm not going to deal with problem 4. I'll only talk about problem 1. I'll just make sure that I don't exceed time. I think I need to go fast. Okay, so the problem 1 is basically a problem of material science, fractional mechanics, and then which we apply in earthquake sources. So if you I mean, some of you might have those who understand the crack theory, or those who have read it through your graduation or post-graduation. So there are 3 mode of cracks which we generally see in fracture and fatigue mechanics. One is the opening mode 1 crack, which is crack opening. Now this is kind of so you're trying to push something from below, for example the lava or magma, and because of which the cracks are opening. So that's the mode 1 opening crack. And then you have in plane shear. So that the contact between the 2 surfaces is still there, but the upper block has moved inside, causing deformation here, but the 2 surfaces are still together, and it's kind of a in plane shear. This is out of plane shear. That means here it's not the inside motion, but it's the sideways motion. So this is kind of we prefer to call as dip slip motion, in which the motion is occurring on the surface, but in the dip direction. This is a kind of strike slip motion, in which we are saying that the motion is kind of sideways. So this also defines the fault categorization we call as normal fault, thrust fault, reverse fault, strike slip fault, dextral slip, sinistra slip. I don't want to go into that detail because that may not be of interest here. So these are the essentially 3 mode of fracture or mode of cracks. And here is your favorite slide, which you people enjoy looking at mathematics. We have this joke here that these mathematicians they they eat mathematical equation in their breakfast, rather than eating. We people from those who apply their mathematics, we use their application rather than eating these equations. So these whole thing, crack theory or fatigue fracture, it started from, in seismology, it started from Volterra formula, and what it does is it relates the displacement at the surface or at any, or even at depth, with the strain nuclei here. You can see lambda and mu here, right? So it relates these two, and it allows me. I'm not going to read all this. It allows me to calculate the surface deformation caused by a dislocation at depth. That's the essence of it. And then we, depending upon what kind of mode of crack it is, I can basically I'm sorry. In case of earthquake seismology, we generally deal with these two kind of cracks. This is generally done in volcanic region where you have crack opening, or in explosion seismology where you have nuclear test where suddenly from all sides the rocks are pushed away. So there's something kind of opening of cavity, or there's sometimes it's cavity collapse. So it's rather than opening, it's called closing. So it's a cavity collapse is nothing but the negative of opening. But in earthquake seismology, it's basically these two kind of cracks. So there's something called strike-slip fault, in which the motion is in plane, but not in the dip direction, but along the strike direction. And then you have motion which is dip-slip fault, in which you are trying to relate the surface displacement or displacement at even at depth with the motion which is happening. So this is depth here, x3, and this is a plane so you have elastic medium below your feet, and there's a plane here along which the motion is going to happen, and this is the upper edge of it, this is the down dip edge of it, this is the dip of this plane, and this is the fault plane. And depending upon what kind of motion it is, we try to calculate the displacement at surface. These are big formulation, and believe me that during my PhD thesis, this is what we were asked to derive. And being we did our bachelor's graduation using mathematics, but we were not tuned to deal with such a heavy mathematics of this kind. But nevertheless, in those days I couldn't stand it. So this is what happens. So this dislocation here, this deformation here during the earthquake is nothing but the one which is predicted by these equations. And as you see that as you move away from the fault, as you move away from the source, the deformation decreases. When you are close to the fault, the deformation is high here. So that means, if I don't have a picture to draw all this the deformation because that's not my intention, but I'll give you some examples here how this formulation has been used to understand various intricacies of earthquake occurrence processes. So I'll start giving you examples how this has been used in our studies. So first I'll give you an example of how the strain accumulates, on the fault, which we can capture through our observation, and then we can actually apply this elastic dislocation theory to understand the strain accumulation. So this is so what we do is we use GPS, global positioning system. Our GPS is very precise. It gives an accuracy of millimeter level, and then we try to occupy several points here. We keep monitoring the coordinate of these points, and then we look at how the displacement is taking place at all these places. And what you see here is, by the way, this is where the Dehradun is, the place where myself and Piyush graduated, did PhD also, is somewhere here. This should be Haridwar somewhere here, and Roorkee should be somewhere here. So that's where from we came. If you look at these arrows here, so this is the Himalayan mountain. This is the India-China border. So this must be Badrinath here. This is where the recent tragedy happened on 7th, if I remember, where avalanche and landslide took place. So what I'm trying to show here is that when you move in the north, the size of the arrow is increasing. The size of the arrow is increasing as you're moving towards north. So there is a gradual increase in the size of this arrows, and that's an indication of strain accumulation, because that's what elastic dislocation theory tells us. So you can actually, so if you try to rotate this picture clockwise and see it and try to compare the elastic dislocation theory, that's where the fault is, right? And on this side, so the blocks on this side are pushed in this direction, blocks on that side are pushed in that direction. So that's the strain curve here. And that's the indication that strain is accumulating in this region. Then we try to model it. We try to see what are where is the fault. I'm saying that we use elastic dislocation theory here, again using Volterra formula. So that's how we use this mathematics in understanding the elastic strain accumulation. I give you another example. Another example is for this elastic strain release, that can I monitor this deformation on the surface, and can I see that as I move away from the fault, the deformation actually decreases. So this is occurrence of an earthquake, and I have picked up an example here, which is there was an earthquake in 2012, which occurred in the Indian Ocean. So the earthquake source was a bit complex, but let's not go into the complexity. Let's look at these arrows. By the way, these arrows are only showing you the direction because there's so much of problem of scale saturation. So we have so between here, these are varying between 25. This is the contour interval is non-uniform here. And what you see here, so I have observations at several places, for example, in Sri Lanka, for example, in Andaman Nicobar. Now, these are the observations of deformation caused by the earthquake. The black vectors here, all the black vectors are actually the observations of deformation caused by the earthquake. So I have observation here in Andaman Nicobar, in Sumatra region. I have lots of observations. I'm not showing it here because I have lots of observations here. And then at Singapore, I have a few observations in the Indian Ocean. And if I try to use the elastic dislocation theory here and try to predict the deformation caused at all these places, it actually matches perfectly well with the observation. The red vector here is the model, the simulated displacement caused by this earthquake, and the black one is the observation. And you can see a clear correspondence between the two. So that means the elastic dislocation theory or the Volterra formula, it works perfectly fine. It works well to understand the earthquake mechanics, to understand the earthquake deformation, to understand the earthquake processes. So that's the power of this mathematical formulation. I can also go on to what I can do is I can take the derivative of these displacement in terms of spatial derivative as well as time derivative, and can calculate the stress, and then try to look at the stress evolution over time as to how the stress has taken place, stress increase or decrease has taken place over time in a region. So this has been done at several places, and one of the and the biggest we use Hooke's law here, which is basically which relates the stress with the strain, and of course it's a tensor, and in the most analyzed form it has got 81 components. But then we can simplify it. We can assume homogeneous, we can assume isotropic, we can assume half space, we can assume symmetry, and then finally we say that okay, these are 6 components, and then we calculate them on plane. So we only deal with shear stress and normal stress. So that's how we try to simplify things, starting from a very complex mathematics. So so this is a very good example in which what people saw was that how a fault has failed progressively with time. So there was an earthquake in 1999. People calculated stress caused by this, and the hot colors here are the stress increase. And look at the earthquake. The next earthquake in 1942 actually occurred in the high stress region. Then they again calculated the stress caused by this and by this, and then the next earthquake occurred here. So this was there was an earthquake in 1943, and then they included the contribution of this, and then the next earthquake occurred in 1944, which is again at the tip of this fault. So that's how the stress evolution takes place, and you can actually see that how these faults are loading the nearby faults by increasing the stress on that fault. We did the same thing in case of Andaman Sumatra region, but I think I'll not go into detail of it because it's already 12:13 now. But it's the same thing what has been done here. And so the power here is that you can look at this deformation in terms of displacement or in terms of stress, and you can use the concept of elastic dislocation theory using Volter formula, and you can have a better understanding of earthquake process by looking at these mathematical formulation. I think I'll stop it here. Thank you very much. And I again say that it could be a very primitive mathematics for you, but that's how we use mathematics in our seismological. It's just a glimpse of it. I chose this example because I'm involved in it, but then there are several other fields of seismology where people use mathematical formulation, whether it is understanding the source, whether it's understanding the wave propagation, or the flow through polar elastic media, what Peter just made a presentation. So, and then people who deal with a statistical model, they use all these mathematical formulation quite extensively. So there is as I said, that it is a script which everybody has to use. The script of physics, the physics laws, is basically the mathematical formulation, and that's where we can use it anywhere. I think I'll stop here. Thank you very much. I'm not here.
Thank you, sir. Before I give a final thank you to you, I'll just, if you have time, I can just say 1 or 2 lines. Hello, sir.
Yeah, please.
Professor Michio Kaku, his statements are very popular about mathematicians. He says mathematicians created amazing edifice within topology that they were sure would never be used, but physicists later found their use for them. So that's what mathematicians, many people tell about mathematicians, or mathematicians themselves say that mathematicians pride themselves being useless. That's another very famous statement by Professor Kaku. But your lecture today, which I was expecting, and that's why I requested you, and you accepted. Thank you for saying. You started from elastic rebound theory, and then moving to plate tectonics and fracture mechanics, and the application of Volter equation in earthquake prediction. It's a clear-cut example that how mathematicians should move to the pure, you can say, pure mathematics and applied mathematics area should be taken. and then they should experiment. It will take some time, but I will refer a quote of a very famous scientist from India itself. He says that if you want to develop an area, so it takes around 2.5 years, and that has been my experience also. So do not fear in going to new areas. That will give you a lot. It may take time initially, but mathematics is really useful, and we all very proud. Thank you, sir. Thank you for being with us, and I am very again proud to have here Professor S.K. Jain, Sir Jain, sir, as we proudly call him in our days, listening our lecture. Thank you, sir.
Thank you.
We are going to start another lecture. Sir, you can go offline if needed, but I request if you want, you can be here. Sir. We are starting another lecture by Mr. Ankur and Pawan Kumar Shah, who is our conference secretary. He will be giving his introduction.
Okay, now, so it is a great pleasure for us to invite our next speaker, Dr. Ankur Kanodia sir, who is going to talk about the option pricing. Before we start this session, first of all, a warm welcome to speaker Dr. Ankur Kanodia sir in this mathematics seminar in science and engineering applications. Also, on the behalf of Department of Mathematics, BIT Mesra, I want to thank you, sir, that you have accepted our invitation as a speaker.
Yeah, thank
now, ladies and gentlemen, I would like to give a small introduction of our speaker. Dr. Ankur Kanodia sir is currently an assistant professor in the Department of Mathematics at National Institute of Technology, Rourkela. Before joining Rourkela, sir has also worked as an assistant professor under TCube 3 at our institute, BIT Mesra, Ranchi. Sir earned his doctorate degree in mathematics from Indian Institute of Technology, Guwahati. Sir is expert in many areas of mathematics, and his main area of research is computational finance. Sir has published a good number of research papers in the reputed journal, and he is also identified as an expert in financial mathematics. He has delivered several invited talks like data science, analytics, LaTeX, machine learning in various institutes across the India. So now, if I say more about him, probably the whole session will be less. So I end your introduction, sir, with this word. And now, over to you, Mike, to sir, and you can start your presentation, sir. So thank you.
Thank you, Pawan. So my screen is visible to everyone?
Yes, sir.
Okay, fine. So the topic of my today's talk is option pricing. So first I will explain what is option and what is the meaning of the pricing here. So I will go one by one. So these are the outline of my talk. We'll see some black source model, which by using that we will calculate or will evaluate this pricing. We'll see the analytic solution. And if time permit, I will go to the numerical methods also. So let's start some investment options. So these are some investment options available in India. I rank them in terms of higher profit, higher risk. So if you invest some amount in the bank, you will get definitely less interest than if you do the fixed deposit or recurring deposit, or you are investing in the bond. That bond can be the government bond or corporate bond. So this list, all are the options are available in India at least. Some employment provident fund, PPF, public provident fund, LIC, Life Insurance Corporation, and recently this government launched this national pension scheme also. Then if you want higher return, you have to approach to the mutual fund, stock market, some shares you can buy and sell. And then the seventh one is the future and options. So today's topic is all about options. So definitely this order in terms of higher profit, so definitely risk is also more. So we'll see what is option. So it is a contract between two parties. So there are two parties. One is called, I'm calling it is party A and party B. So it is a contract between these two parties, and the definition of the option is it is a security or it is a contract between the party which gives honor, right, but not the obligation to buy or sell the underlying security on or before a predetermined future date for a pre-specified price. So let us understand this by one example, then I will come to this definition later. So suppose you want to buy a gold. You have money, you want to buy a gold, you will go to the shop, you will purchase the gold and you will get the gold. So this is one type of buying or selling. You want to sell, you will go to the shop, you can sell and you will get the money. But now what we will do, so currently in India, the gold price is around 48,000. Suppose you want to buy the gold and that gold is not required immediately. Maybe 6 months later, you need that gold. So what you will do, you will go to the shop and you will make a contract or you will book the gold that after 6 months you will come and you will purchase the gold. You will go to the shop and you will talk, okay, this is, so they will tell about the gold price. So for example, suppose I am taking, it is currently some 48,500. So for rough estimate, I am taking 48,000. So after 6 months, it may happen that gold price will increase. It will reach to 50,000 or 52,000, or it may decrease also. From 48, it can reduce to 46. Even it can reduce to 40,000. We don't know. So suppose we will buy today, and if it will increase, then we are in profit. But if we buy today and it will decrease, then we are in loss. And for the timing, suppose it is not required, we need that gold after 6 months. So what we will do, we'll book the gold to that owner or that shopkeeper. And we will decide the price also, that okay, we will come after 6 months and we'll buy that price, not this 48. Maybe it will increase or decrease, doesn't matter. That owner will also agree, okay. So depending on the scenario, we'll buy that gold for the pre-specified price. So that price we will decide now, and the transaction will happen in future for that particular price. So for example, suppose we decided that we will buy the gold at price 46,000. So irrespective of gold price will go up or down, the transaction will happen with the price of 46,000. So after 6 months, if you go there in that shop, and if price is increased, suppose it is reached to 50,000, so definitely you will buy at 46,000 because you are getting at the cheaper price, and that deal you made as of now, and the transaction is happening in the future after 6 months. But suppose price is decreased, so you agree with the 46,000 and it is decreased, suppose 40,000 or 41,000. So definitely you are getting a cheaper price in the market, whatever deal you did with that particular shop, like 46,000. So definitely you will not going to buy at 46,000 because it is already available in the market at the cheaper price. And then what you will do, you can go at and visit any other shop and you can purchase the gold at the cheaper price. So that deal, whatever deal you are making, that you will come in the future after 6 months and you will buy that gold. That deal, that contract is called option. So what we are purchasing, buying and selling. So that formal definition here, I will explain what is this option. Option is a security which gives honor. So once you will do this contract, then the honor of that contract, it will have that honor of the contract will get some right, but not the obligation. Not the obligation means that is the honor which he want to buy or sell that gold with the pre-specified price. That pre-specified price we will decide today, and that predetermined future date also, like after 6 months in this example of gold. So that is the future date we will determine, like we will predetermine, that is also fixed, and that price is also fixed, like which price the transaction will happen and which date it will happen on or before that we can perform this. After that 6 months we will go, then this contract will expire and then we cannot do anything. So it will give the flexibility to the owner to buy or sell. So that owner can buy the buy contract, then you will buy. If it is the selling contract, you will sell. And both the party will agree with that which date the transaction will happen, at which price it will happen. So the party which has right but not the obligation is called the holder of the option. The counterparty is called the writer of the option. So writer of the option doesn't have any right but only the obligation. If the holder of the option, the party A, will demand that, okay, I want to buy, then the second party will agree to give, buy or sell that things at that pre-specified price. So that is the option. Since in the option we have right, like if we are getting the cheaper price in the market, definitely will not buy at the higher price, like I explained in the gold example. So we have the option, that's why it is called option. This contact name is called option because we have the choice, we have to buy or not. That is depending on the situation. If we will not buy, doesn't matter. If we will buy, then also no problem. So here we are getting an option, we are getting a choice. So that's why its name is option. So based on the you want to buy or sell, you have to do the contract of call option. Call option gives the holder right to buy. Like if you want to buy the gold, then you will sign a call option. If you want to sell, you will sign a put option. So call option will give the holder right to buy, and put option will give the holder right to sell. And the amount which you agree today, at that amount the transaction will happen, that amount is called strike price. And the date on or before that transaction you can do, that is called expiration date. So let us understand this by example. Suppose that contract or that call option you sign for a share. You want to buy a share. Instead of gold, you can buy share. So that contract you can put for any other underlying asset also, like you want to buy gold, you want to buy oil, or you want to buy some currency, some other underlying asset also you can do the same thing. So the only thing is that the underlying asset will change. So in this example, I took the underlying asset as a stock of some company. You want to buy some share. So at time t equal to 0, that company share price is 100 rupees. And you went and you agree that after some time, after 1 month or within 1 month, you will buy this share at price 110. So that 1 month on or before also you can do. It's not like that you have to wait till the last date of 1 month. So in that case, what will happen, because you have call option, that means you can buy on or before this 1 month. So if price will increase, suppose price of this share at time t equal to 0 means at day 1 when the contract will start, suppose it increased to 120, then what you will do, you will purchase at 110, because in that contract they are agreed to sell, because you have the contract to buy. So you can buy at 110 rupees and you can sell immediately in the market, and you will get the profit 10 rupees, because in market price is 120. Suppose market is going, this market price is going down, like from 100 it will become 90, then what you will do, you will not do anything, no need to buy, so no problem. So this is what I am talking in the party A point of view. Then what is the benefit of party B, which party will agree to do this? Similarly, if we consider the put option, suppose again the same scenario. In this case, if price will decrease 90 rupees, this is the option, put option, that means you can sell. Which price you can sell? 110. That is the selling contract. So if price is less than 110 in the market, so what you will do, you will immediately purchase the things from the market and you will sell at 110 rupees if it is less than. Suppose market price is 105 or 90 rupees, you can purchase easily at 90 rupees and you can sell at 110 rupees, because they agree that contract. So in buy option, if you are signing call option, that means you are agreeing with the buying. If you are agree with the sell, like both the contract, you can get benefit depending on the price will go up or down. And if you are in the loss, then you will not do anything, and then after 1 month that option will expire, that contract will automatic over, because that contract is for 1 month only. So based on this exercising or based on this transaction of that contract, whenever you will do, Options are two types. One is called European option, another one is American option. So in European option, it can be exercised only on the expiration date. The last day of this expiry, that day only you can do that transaction. But in American option, it will give the flexibility that at any time period to that or including that expiration date, you can do the transaction. So that is the flexibility in the American option. So if you sign American option, then you have the flexibility. And in case of American option, so definitely for American option, that option will be more complicated than European option. We will see a little bit later. So now we'll talk about the other party. This is whatever till now we have discussed. This is the one party. If you go in the call option or put option, you will get right to buy, and that is your wish. You want to buy or sell depending on the situation. So that is your benefit. But what the other party will get the benefit? So like in case of the gold example, you will go to the shopkeeper, you will agree this amount, you will come and you will buy. So that if price is less, then you can go directly to the market and you will purchase. If price is more, you will get the cheaper price using that contract. So what other party will do? So for other party, if you agree with this contract, you have to give some amount. Like if you are to ensure that you will come and buy. So that booking amount, you can give whatever they will agree. That booking amount you can give, and that will give the guarantee that okay, you will come after 6 months or within 6 months you will come and you will buy the gold. So something similar to that, if you are doing share, the contract on share or the contract on the exchange, this currency or any oil, anything commodity. So in that case, you have to pay some amount, and that is called the premium or the price of the option. So definitely American option have the more flexibility because you can exercise or you can do the transaction at any time period to that. So the premium for American contract will be more as compared to the European, because the extra leverage in the American option is that you can perform the transaction at any time period to the expiration date. So today's topic is that how to get the true value of the premium, like how you will decide you are not paying the more premium, what will be the correct value of the premium, how we will decide what will the price or what is the premium amount or what is the value of that option. So now before going to that, the question is why options are not traded? Like if you want to buy some share, you can directly go and buy the share, but what is the need of this contract? What is the advantage of that contract? Suppose you want to buy 100 share of any company and that price is 50 rupees. So total money required for buying 100 share, per share price is 50 rupees. So total you will get 5,000 rupees. Total 5,000 rupees is needed to buy 100 share of that company. The same thing we will do by this option. If we sign a contract that in the future we will buy at, we will decide which price, then the same thing you can get even less than 200 rupees. That 100 share we are not actually buying, that we will buy depending on the situation. That contract we can get less than 200 rupees. So that is the huge difference of in terms of the money. So 100 share physically if you want to buy, actually you want to buy, then you have to give 5,000 rupees. But here within 200 you will get this 100 share. So this is one advantage. Another advantage is that suppose market crashes and the price will become 50 to 40 rupees, then total loss you will get 1,000 rupees. And here in this contract, whatever will happen, you can lose maximum 200 rupees. Like how much premium you paid, that premium will only gone. Remaining amount will not get. So maximum loss here is 200 rupees if the premium is 200. But in terms of profit, if you talk, suppose the price is increased from 50 to 60. So by investing the actual scenario, by investing 5,000, if it will increase to 60, it will become 6,000 and you got a profit of 1,000 rupees. By investing 5,000, you are getting profit of 1,000. But here, if it will increase 50 to 60, and suppose you sign a contract at 55, then 5 rupees profit per share, you will get 500 rupees profit just by investing 200 rupees. So you are getting a profit more than double in case of option. But in case of you are getting, by investing 5,000, you are getting 1,000 rupees profit. So that is also one way why options are more popular and why people are interested in the option. So let us first deal with the European option. Here we can do the transaction only at the expiration time. That means we cannot do transaction before the expiry. Only on the expiration date we can do the transaction. So how much profit we will get in this case? Suppose we are doing this contract on the stock and its price at time t is ST, because it is a European call type of option, and we agree that the transaction will happen at this amount, strike price is K, and the expiration date is capital T. So at capital T, what will happen? There are two possibilities. If the stock price is less than K, then we will not do anything, we will not buy, and the option will expire. If it is increased, then in that case we'll make a profit of ST minus K, because it is increased. So we'll buy at price K and we'll sell in the market immediately at the price ST, because ST is the, as capital T is the price, market price. So we'll get the profit of ST minus K. So in the both the case, if we combine, we'll get the profit of ST minus K comma 0. In the first case, we will get the profit 0 because we didn't perform any transaction, and in the second case, we'll get the profit of ST minus K if we are doing European call option. Something similar to that, if we are doing European put option, the same case, then if ST is less than K, we are getting the cheaper price. So what we will do, we'll immediately purchase from the market at this ST price and we'll sell in that contract at price K and we'll get the profit of K minus ST. If the case is reverse, we will not perform any transaction, that profit is 0. So in this case, we'll get a profit of K minus ST comma 0, the maximum of these two values. So now we'll see how to model this, like how to get the actual premium value or the value of the option so that you can pay that amount in order to buy European call or European put. Later we will go to the American also. So that is the question, how much premium should be paid by the holder at time t equal to 0 in order to get this profit for call option and this profit for put option at time capital T. So this is the problem for pricing of the option. So there is one principle that is called arbitrage principle. Arbitrage means that the existence of opportunity to make a risk-free profit, like without money, zero means like without money, like with zero money, can you gain the positive profit or not? So such scenario will not exist. So we'll make this assumption that there is a no arbitrage in real market. It exists for some small period of time. So for our this theory point of view, we'll assume that there is a no arbitrage exist. That means there is no opportunity we can make a risk-free profit. So this put call parity is the relation between call price and put price. Like whatever the premium you are putting for European call, the C represents for European call price and P represents for European put option. So this is the relation between European call and European put. So here K is the strike price, R is the interest rate, and S0 is the underlying asset price at time t equal to 0. So you can do this proof also. So in this case, one call option and this much amount if you invest in the bank for period of capital T, and in this case one put option and this is the initial amount of this. So in both the cases at time capital T, what you will get at time capital T, because the call option, you will get the profit of ST minus K comma 0, and if this amount you will invest in the bank after time T, because of R is the compound interest, will calculate continuously compound interest, then you will get from bank amount K, then total profit in this first case you will get maximum of ST minus K. In the second case it is put option, so you will get K minus ST comma 0, and this 1 unit price at time t equal to 0 is just 0. At time t equal to capital T, it will become ST. Then in this case also you are getting the same profit. So from using this arbitrage principle, we can say that these both are equal, because if one is greater, then there is a arbitrage opportunity because both are giving the same profit. So arbitrage opportunity will exist. So by arbitrage principle, we can say that this is the relation between call option and put option. That means C minus P equal to S0 minus K to the power minus R capital T. So in case of American option, This put called parity estimate in terms of inequality is this one. This is also we can prove by arbitrage principle. If it is less than that, then there is an arbitrage opportunity which will not exist. So this American option will also follow this inequality. So if we know the price of call, we can get at least idea about the what will be the price of put. So now we'll go in terms of the pricing. So whatever underlying asset can be gold also, it can be oil also, it can be some currency also, it can be some share or stock price. So these are some random number because we don't know what will happen in future. So this is not like deterministic, it is random things, stochastic. So this, for that we will assume that this price of that underlying asset will follow this geometrical bounding motion or GBM model. So this will followed by this differential stochastic differential equation dst equal to mu st dt plus sigma st dwt, where mu is the drift, sigma is the volatility, st is the stock price at time capital T, and wt is the Wiener process. So for our model, we will assume mu and sigma are constant. It can be some function of time also. It can be the function of s also. Then the model will become more complicated. So we'll first see the basic model for this. So what is the Wiener process? Is a time continuous stochastic process which will satisfy this property W0 equal to 0 with probability 1. Wt follows normal distribution with mean 0 and variance t. And for non-overlapping interval, this difference are independent. So these are some result about this Wiener process. So by using Ito's lemma, we'll develop a model for pricing of the option. So what is the Ito's lemma? It is a stochastic version of the chain rule in the calculus, like whatever we have chain rule in the calculus. So this one is the stochastic version of chain rule. So if x is a stochastic process which will satisfy this stochastic differential equation, then for any function, smooth function from R2 to R, that means partial derivative will exist and continuous. This for this function will follow this one, df equal to ft plus afx plus half b square plus second derivative respect to x plus b fx dwt. So by using this Ito's lemma, we will develop a model for pricing the option, and that model is called the Black-Scholes model. So from Ito's lemma, this one application of Ito's lemma, if st is the stock price, then it is by Ito's lemma we can write like this. So we can get the stock price at any time t by using this formula. So here Wt is the Wiener process, that means it is some normal distribution. So based on some sample, we can generate even different path for random path for stock price. So based on that also some methods are there, that is called Monte Carlo method. Based on this, that we will not discuss here. So now we'll see what is the Black-Scholes model for pricing this option. So this is the first model developed by this Black and Scholes. Later Merton also contributed something in this model. So this is also called Black-Scholes-Merton model, and it was first widely used for option pricing. So in this model, they assume that this current stock price, expected dividend, this option stock price, expected interest rate, and time of expiration, and the volatility, everything they took in this model, and they consider the sigma and mu are constant. This drift and this volatility are constant. So this is the most well-known model, and they published in the paper in 1973 in the Journal of Political Economy. The title of this paper was The Pricing of Option and the Corporate Liability. So later, in 1997, they received this, unfortunately Black passed away, and then this Scholes and Merton, they received this Nobel Prize in the field of economics in 1997 for this work. So what is this model? So suppose this is the option value. Irrespective of it is call or put, I am developing a model which will give the price of the option. So V is the price of the option. So it will depend on S and T because the sigma, mu are all constant in this model they assume. So this long option means you have to buy. Then short means you have to sell. Buy. And if you buy this one option, that price is V, that we have to find actually at S, T. and this delta unit of this underlying asset S. So this option on this stock, so this S, suppose if it is gold, then this is the S is the price of gold. If it is stock, then it is the price of stock. So delta unit of that quantity S with the price S, it will give the delta S. So this much you are selling. Short selling means you will borrow from someone and then you are selling. So total amount you have pi. Then by short selling means you have to first borrow from someone and then sell it. Later you will purchase and return to that person. So that is the concept of short selling. So in that case, you will get pi plus delta S is equal to this whole amount, whatever you got, that you invested in the option. That means that is the price of VS option. That can be call or put. So the pi equal to V minus delta S, because S is follows log normal in this model. So the stochastic differential equation for S will be mu st dt plus sigma s dwt. So now we'll find the change in this d pi, that will give dv minus delta times ds. So this dv will replace by Ito's, and this ds will use this one. So what we will do, so by Ito's lemma, we'll get dv, will get this one, and that dv will replace in the form of d pi. So we'll get this equation. So here this dt and this, all those first two terms are deterministic, and this is the stock price, that is the random. So in order to remove this random term, we'll set up this delta equal to, this is called hedging parameter. We'll set up this delta as a del v by del s. Once we'll set up this del v by del s, this whole quantity will 0, and that will become normal deterministic things, not a random. So this amount, this pi amount, if you invest the same amount in bank, because in bank there is no risk. So there is no risk here, there is no random things here. So the same thing, by investing in the bank with the interest rate R, will get R pi dt in times dt. So both, when we equate, what we will get this famous Black-Scholes equation, which they given in 1973. So here V is the price of that option, S is the underlying assets, and this T is the time, R is the interest rate, sigma is the volatility. So by solving this, we'll get the value of the option, and depending on it is call and put, so we'll choose the appropriate boundary and initial condition for solving this. So the time is from 0 to capital T, means when it will expire the from 0, and it can be infinite. So in that domain, we have to solve this. So these are some assumptions we assume, or they assume for this model, that it can, this is only for European, it can be exercised only at the expiration time. No dividend are paid. That means there is no hidden charges, there is no transaction charges if you are doing this, buying this option in the exchange, and the risk-free rate and volatility are known, and these are constant in this model, and this return are normal distribution. Under this assumption, this is the model equation for option pricing. So this we can solve. If it is European call, then we will take this as a final condition. So this PD is the backward PD, not in the forward PD. So it will from capital T to 0. We have to do the backward calculation. So at capital T, how much we will get? This is the profit maximum of S minus K, comma 0 in case of call option. In case of put option, so it will take this condition, this final condition with that PD, with appropriate boundary condition, we will get the price of European call. If we take this condition, then we will get with the appropriate boundary condition, then we will get the price of put option. Similarly, other options are also available. So I will not go into much detail about this. Like if digital call option, then this is the payoff or profit. This is the for digital put. Similarly, bull spread is there. Here two strike price K1, K2 is there. Bear spread, straddle, strangle, butterfly, and this. So I'm not going to those things. So these type of options are also available. So for solving this, we need the boundary condition. So these are the boundary condition will apply when stock price is 0. So definitely this European call price is also 0. So this C is 0. If it is S tending to infinity, then this is will take that right boundary. Similarly for put, by using this put call parity, we can get the boundary condition for put option. So that's Black-Scholes equation combined with this final condition and this boundary condition, we will get the solution, or will get the price of that option. So because it is a linear PD, so we can solve, but for some other option, for American option, it is more complicated, non-linear. So we cannot have the analytic solution, but in this case, we have an analytic solution. So by using this transformation, that Black-Scholes PD will convert into the diffusion equation, heat equation, And we know how to solve the heat equation. So in terms of green function, by using that green function, we can solve, and the price of call option will come this one, where D1, D2 is given by this, and this is the CDF of normal distribution. So this is the price of European call. By put call parity, we can get the price of put option also. So no need to solve again that PD. By using that relation between put and call, you can find the price of put option. So this we can do in the just basic simple model, but if model is more complicated, we even don't have the analytic solution, then we have to go towards the numerical method. So I'm not going to much detail. I will just show the result only. So there are popular numerical method available for this solving this PDE. One is finite difference method or finite element method. Binomial method is the discrete version, and this is based on this stochastic differential equation. So this Monte Carlo method is widely used by the industries, and this finite difference, finite element, and this binomial method, such are using this mostly. So I will directly jump to the result. So there are some schemes in the finite difference setup, explicit scheme. So this is the result. So for European call option, if you are using explicit method, that means the forward in time and central in space, by using the appropriate boundary condition, whatever we have, and with the final condition. So this blue is the final payoff at the time capital T. Once the time will move, so this is the price or the value of the option once the time will move. So this one is for time capital T, and this one is for time T equal to 0. So from time capital T, that means the expiry date, we will do the backward calculation and we'll reach to the time T equal to 0. So that we will come to know for today, if you want to go for signing this contract, then how much amount we have to pay. So this is the 3D version of payoff with respect to time. So the implicit scheme also will give the something similar to that. In that case, we have to solve this system of linear equations. So now we'll come to the American option. So how to deal with the American option, because the option at any time before on or before the expiry date. So to ensure that, because American option have more premium because it has a more flexibility. So what we will do, we will solve this something similar to the European option, but we'll impose this extra condition, like whatever profit or payoff we'll get in the European option, the American option profit will be more than this. So this condition will impose during our numerical simulation, so that will ensure that the American price is always greater than this, because here we are definitely get more return as compared to this. So this condition will apply, and if we don't want to apply this, then we have to solve this partial differential equation, whatever Black-Scholes equation we are getting, in the inequality form, not this equal to 0. It will be some greater than 0. So we have to go to the some complementary problem to solve that PD. So this is the condition we will assume in order to calculate this American option price by using explicit method. Something similar to that we can do for implicit method, even some Crank-Nicholson or some other finite difference scheme. So this is the comparison between European and American option. So clearly we can see that this American is more than this European. This red line is, this red curve is bigger than or higher than blue curve at any point of this. So the more complicated way, like so far whatever we have seen, we assume that R is constant and everything is that there is no transaction charge. If we'll assume that some transaction charges are there, dividend is also paid, so some different terms will come. So if the different version of this Black-Scholes equation, if the dividend is paid yearly or on what basis, then the Black-Scholes PD in this case will become, this extra term will come here, R minus T. So we have to solve here. This variable is also not a constant, it is a variable coefficient PD. If that option is on this foreign currency or any currency, then this interest will also come. So this is the modified version of the Black-Scholes equation in case of currency option. In case of commodity, like if you are buying some gold, oil, all those things, then the cost of carry is also included, and then this is the modified version of Black-Scholes equation. If the option is on future, then this is the PDE. Similarly, if it is time dependent parameter, there is a power option, 2-factor. Early exercise means you can exercise at any time. One is American, Bermudan is also there, but in Bermudan option, during the time interval from 0 to 2, there is some time point, like you cannot exercise at any time, but they will specify like after this, like after 5 days you can do, or after 1 week. So every week they will give 1 week, 1 day, like every Thursday you can do. So that is the Bermudan option. So they will give some specified time point, that time only you can do the exercise. So it is between the European and American. Like European, you can exercise or do the transaction only at the final time. American, you can do at any time, but in Bermudan, you can do at specified time. And there are other also options are available. So that's all. So these are some references. So if you have any question, you can ask.
Hello. Thank you, Dr. Ankur. This is Piyush Tiwari here from VIT. Thank you for accepting our invitation and being so humble that you try to help us every time that small things we ask you. Now it's over to us.
So thank you very much, sir, for the nice presentation. And really, this session was very interesting and informative for all of us in this mathematics seminar on science and engineering application. So once again, thank you very much, sir.
Thank you.
So now we are going to close this first session. So now we will meet at 2 o'clock. So all of the participants as well as guests, please join at 2 o'clock. So thank you very much.